Okay, welcome everyone to a re-recording of a talk that was presented January 23rd at Penn as part of the Philadelphia Dynamo user group. So unfortunately, Penn's firewall was blocking our stream, and we had to actually do the first talk from an iPhone. But luckily, we did capture Daniel's presentation, Daniel from Ballinger. And when it came time for this presentation, our luck kind of ran out and the phone died. So I'm going to be re-recording this for you right now. And actually, it should be a little bit better because I'm on a desktop. So the performance should be a bit smoother, should let me step through the code a little bit more easy and with some more fluidity. And I'll have a little bit more time as well to spend on some of the more nuanced and advanced topics that we get into. So let's get into it. So the audience at Penn was obviously a little bit different than our typical user group meetings in that they don't have much experience with Dynamo or Revit for that matter. They're students, right? They play around with Grasshopper, they play around with Rhino, but building information modeling is kind of a little bit too much to get into in that stage of your professional development. So we wanted to present this in a way that was contextualized and informative and really set the stage for later part of the presentation. So when thinking about what is Dynamo, I really like to start with the definitions that Autodesk gives us. I think it's pretty interesting to hear from the creators how they define what they've created, how they define their own tool. So Dynamo's definition is community-driven, open source graphical programming for design. And Dynamo Studio is listed as computational BIM design software. These two obviously being separate pieces of software, Dynamo BIM being directly tied to Revit, and Dynamo Studio being a standalone package which doesn't really interact with Revit or building information modeling. In my opinion, it actually just lets you work with some geometries and set up logic and routines in a somewhat siloed environment. It can still obviously interact with packages, interact with other pieces that regular Dynamo and Revit can, but more standalone. So when we then get into the specifics of their definition, we see that it gets a little bit richer. There's some more detail, and I don't like to spend so much time on the full wall of text. I kind of go one step further and just highlight some of the things that stand out to me that I think are important. So the takeaways I think are that obviously this is a platform for graphical programming. It's open source. There's a friendly visual interface, and you essentially can do things like construct logic routines, automate tasks, design workflows, so on and so forth, foster interoperability, and all of that. So I also then like to go one last step further and just go ahead and combine all of it together into one definition and recognize that Dynamo is generally a graphic programming platform for the architecture, engineering, and construction industry. And my kind of more nuanced definition is that it's a graphic programming platform which extends Revit's building information modeling capabilities by allowing designers to create logic and processes which are built from the information inherent in the model. And again, I did mention that Dynamo Studio is a standalone package, doesn't really link to the information portion of building information modeling, but that doesn't mean that just because the connection isn't explicit, that doesn't mean that you can't make the connection yourself and that it can't be a very, very useful part of your design workflow. And that's part of the reason why, in the end, I like to mash the definitions together because they are separate software packages, but I think they really work together in unison for the best results. And perhaps even going forward, we'll see what Autodesk does, but that convergence might also be something that they're thinking about in one way or another. And so then when we think about the difference, as it's so often talked about between Grasshopper and Dynamo, I actually just like to say that this is the more important difference, and we should just recognize the not necessarily the host platforms, but the parent platforms, and what that means for the host environment. So Rhinoceros is a 3D modeling software. It's used by a lot of different trades, a lot of different professions, sculptors, jewelry designers, everybody and anybody that wants to play with geometry or do certain kinds of analysis. Whereas Revit is much more nuanced, it's much more specialized. It's a coordination and documentation, building information modeling software for the architecture, engineering, and construction industry. And that is, in essence, our context. It kind of gives us a clue as to what we can expect from Dynamo, which, if not always tied directly to Revit, and at the very least, it's born from some of those concepts. It carries some of those concepts throughout its uh, own way of thinking. Um, and conversely, Grasshopper tied to Rhino differently, but similarly. So next portion is what I like to call thinking about the question in the form of an answer. And I think this is inherent in design computation in general, but perhaps especially in visual scripting. And we'll see what we mean by that in a second. First, if I was giving this lecture 6 years ago, this would probably be my next slide, and we'd talk a little bit about poeticizing the ordinary, and we'd have a great time. But unfortunately, somewhere between now and then, I got a real job, and we're going to start talking about this instead. So, question in the form of an answer. What does that mean? Usually, in a process like this is the way I like to think about it. You start with an initial inquiry, initial question. It's pretty simple. You want to do something, or you want to know something from a model or from a design, whatever. Then you take it to the next logical step, which is capturing some of that into a script or a graph. And this diagram is obviously showing the script version that might be something like a programming syntax like Python or whatever, C Sharp, Java, whatever people are comfortable with. But this is just as easily a Dynamo graph or a Grasshopper script. It's absolutely the same. So after you put that intelligence into a piece of replicable logic like the script, you then run it and you get your result. And it's great. It's phenomenal. You're happy. But typically, that really just leads to another question. You set up, let's say, you make your randomized panels in Dynamo or Grasshopper, and as soon as you have that working, you're excited. But now you want to know if that can react to solar constraints, or you want to know if you can extract some information about cost or material takeoffs. So all of a sudden, that initial exploration that gets your feet wet really just pushes you into a more complex method of inquiry. And the good thing about doing a process like this and capturing your intelligence systematically is that when you get that more complex question, you can start with what you've already done and what you already know, and you can just add to it or change it accordingly for that more complex question. And this cycle can really just repeat itself infinitely until your questions are already answered, until every question that you're answering is already captured in this kind of artificial, for lack of a better word, intelligence that you've created for yourself. And that's really what Dynamo does. This is on the left here, we have a Dynamo node, and on the right, we have the contents of that node. This is just to, again, underscore that previous diagram is that a script is not necessarily textual, it can also be visual. And that's why Dynamo and Grasshopper are visual or graphic scripting languages. So we see this custom node here. It contains, I don't know how many pages this is, maybe 24 or something like that of Python code. And that can be changed, that can grow, that can be developed. But for the time being, it holds a lot of work and it holds a lot of history. Just by kind of being here and being available for us to use. So this next portion is somewhat diagrammatic, and I absolutely have to preface this by saying I'm neither an academic nor an architectural historian, but I think some of the concepts that we're going to talk about here are definitely hold true. So first, I want to start and think about the first concept of an architect or a builder. And I've kind of personified this figure in a semi-romantic way with the name of Imhotep, and that's the name, right, that the history books are fond of. But that's not really the important part. It's not the personification. It's just thinking about the first idea of this master builder or this architect, the person that was orchestrating construction, orchestrating design. And we think about that person and we think about how did they communicate their intent? How did they do what they did? It's very much a field presence. So if we think about our specific personified example here, Imhotep, um, you can go online and you can try searching Imhotep floor plans or sections. You're not going to find any. There's no construction drawings. There's no construction documents. The Egyptians did record their construction, but for very different reasons than us. They uh, documented after the fact. They didn't document to create the construction, they documented afterwards. So they would have a record of what happened. And we kind of do both, but first we, of course, document for construction. And so this master architect or this master builder historically is just very much directly in the field, giving directions, telling people what to do, and orchestrating the entire process. And you can really even think of it another way. Let's go back to another point in history. Hammurabi's code is widely considered as one of the first examples of an architectural code. And there is language within that code which says if a builder were to erect a house and the house were to fall and kill the inhabitants, then the builder would be stoned to death. So that language is placing the blame directly on the builder or architect. That's not something that would happen today, right? If we think of a building collapsing, if we think of a tragedy of that magnitude, our initial jump to conclusions might be the structural engineer or the contractor. Maybe there was, issues of quality in the field. But it would never be to jump to the architect and say, what did that guy mess up, right? We implicitly know that that's a responsibility which does not fall within the architect, within the scope of the architect these days. So just another way to think about that separation. Then if we make a leap, somewhat selective, admittedly, leap to Carlos Scarpa, uh, very widely admired and respected architect, I would say, even though there has been some debate between academics as to whether he is deserving of the title of, quote unquote architect. And here's why. It's because he also didn't really draw that much. And if you search online for his drawings or in a library, you will find drawings, absolutely, but they're sketches, they're working drawings, they're layered, they're thick, they're informative, but not in a way that we're familiar with, um, not in the way that we would construct construction documents these days, which are very clean, very technical. And the reason why his drawings are like that is because he was directly in the field. And his drawings were born out of things that were happening in the field. They weren't prescriptive, they were, in a sense, reactive. So, for example, he's out in the field, he sees a mason cutting some brick or some stone, and he goes up to him and he says, hold on, I think there's a better way to do this, or here's how you should be doing it, and starts doing the drawing, starts talking to the person actually doing the work, and together they kind of work through it and create the thing. And as a specific example of that, I'll highlight. Unfortunately, I don't have a picture of it here, but there's a specific Scarpa detail. It's at an interior corner. Many of his interior corners don't meet at a sharp corner. There is a hole. So that's something that's very much born out of field presence. He was on the field. He saw masons cutting tile. He saw that it was incredibly difficult to get a clean rectilinear inside corner when you cut masonry. So rather than continuing to waste their time and waste material, he developed this detail which would really celebrate that point of construction and make it easier for them, and just also represent that in the aesthetics as a celebratory kind of thing, not as a let's hide it because it's ugly. Let's do something to cover it up type of thing. But again, very much born out of things that are coming out in the field. And so lastly, we come to us, the contemporary architect. And we're pretty familiar with our deliverables, right? We do some drawings. Everybody does drawings, I would say, if you're an architect for the most part. These days, we're also creating models as instruments of service in some cases. And there's also vast swaths of project data, which is just kind of floating around here and there, which also holds a portion of the objective truth of that project. And that is things like RFIs, submittals, things that are just floating around in emails that nobody really knows about. It can be anything, but it's a lot of stuff. And so all that this diagram is ultimately trying to say, now that we're kind of at the bottom of it, is that as time's going on, we are making more stuff. We're doing more in order to communicate our intent and in order to make sure that things are happening in the field in the way that we want and in the way that we plan. So we can think of this in also another way. Again, starting at the top, the first architect and slash builder is just that. They are everything. They control everything. We think of that Hammurabi Code example again. The builder is responsible if the house collapses. The builder is responsible for everything, for whether the house looks good, for whether it's comfortable, everything. They are one entity. We then make the jump to Scarpa, and he's not really the master kind of sole genius and responsible party for everything, uh, but he does have direct links to the builders. He's in communication with them. He has control over them. He's in direct contact with them. And then we get to the contemporary architect here at the last stage. And this is a structure that we're a little bit more familiar with, right? We have some consultants, such as MEP, structural, landscape, civil. They come to us with their individual expertise. We conglomerate everything. We package it up, and we're responsible for it. We hand it off to the client. We hand it off to the contractor. And then, as this diagram is showing, the contractor's sending it off to the builders. Obviously, those are the subcontractors, but for the purpose of this diagram, builders. And so when I look at this diagram, I see that as time goes on, the architect is getting farther and farther from that point of construction, from that entity that is building. And we can look at it another way. So there's a gap here, 4,685 years between the first two stages here. And then there is only a gap of 112 years between a relationship that Scarpa had and a relationship that we have. So my personal kind of fear, of course, is that in another 100 years, this diagram may even be farther and farther from where we want it to be. Hopefully that won't be the case. And there's certainly things that we can and should do to facilitate that kind of relationship if we do agree with that. But it's something to think about. It's something to think about, especially when thinking about the Penn crowd, is that when one's in school, you're very much at that first stage, right? You are the master architect, you are the master builder, you're in control of your entire project, and everyone else is could be a willing collaborator, but they might not be. It's kind of up to you. And then you get out of school, and then you're faced with that first employment experience for a lot of people, and you're suddenly transported 5,000 years to a relationship that you're really quite unfamiliar with and somewhat uncomfortable because you're used to being in control. Um, and you really have to be conscious of what you have to do if you still want to have some of that control. And our initial reaction in this stage is to say, I'm still going to tell everybody what to do. I'm still going to try and enact control because I know best. But the reality is that you really can't, right? Because you can't tell subcontractors what they're going to do. You can't even tell the contractor what they're going to do. Means and methods are their own. You can't really dictate that. The same thing with your consultants. You rely on them for information, you rely on them for expertise. And there might be things that you might want them to do, but you can't tell them what to do and how they're going to do it. You can certainly negotiate, but you can't really, again, you can't tell anybody what to do. So this relationship here that we sometimes try to enact in the diagram below doesn't work, and it doesn't work for anybody, especially not for us, but not for any of our partners. So how do we do what we want to do in this modern context of waning agency and increasing project complexity? Well, rather than trying to be prescriptive, collaborative approach is really the best, in my opinion. So rather than trying to tell somebody what they're going to do, a value proposition is infinitely more compelling. A proposition where you say, I have something that I want to do because I think it's going to make the project better, and I think you might have some interest in this because it'll also make the project better, of course, for you, but it'll also save some time, save some money, allow you to spend some of that time and money on another portion of the project, another portion of the design that you want to develop as a specialized entity. And through that collaborative nature, you can really start to get more out of the process. And of course, within the context of this talk, the way that we facilitate that collaboration is through design computation. We share our intelligence with our partners, and we kind of expect or hope that they do the same. So in the beginning stage, there's a sharing of transdisciplinary knowledge and intelligence. And again, this is kind of what I just mentioned. This is maybe offering some information to your MEP consultant, which they would normally perhaps have to recreate themselves, and they might have to, of course, accept that and accept the liability that comes with accepting your information. But if they recognize and trust that it'll save them time, it'll create a more accurate result, and overall contribute to the quality of the project, they would likely be agreeable to that. But it's really up to you to prove the value of sharing your knowledge with them, and to also prove the value of them sharing their knowledge with you. So after that initial stage of sharing, of course, there's that negotiation for mutual benefit, right? And in this diagram, we specifically think about that architect and contractor relationship, because really that's the point of separation. That's where design breaks off, turns into construction, and once it's in construction, it's really almost entirely in the contractor's hands. So every kind of proposal or idea that we have or that we want to enact, it has to be relevant. It has to have benefits for everyone. And of course, if it does, then we realize that design intent in the field, the contractor pushes that out to their subcontractors, or again, as this diagram shows, builders, and hopefully there is benefit realized on all sides. So diagrams aside, let's look at what this actually looks like in a real project. And I think this will really kind of explain what we mean by that collaborative relationship in the context of modern contractual relationships, modern professional relationships, and so on and so forth. So the project we're going to look at is a project by KieranTimberlake, Wellesley Pendleton West. This project was done between 2014 and 2016 and is now completed. So this is just a little bit of an establishing shot here of the project, and I really think this image kind of really begins to speak for itself, just letting it sink in. But we can see that the intervention is in the middle. That's the KieranTimberlake intervention. On the left and the right, we have existing buildings. We can see that they have a little bit more traditional classical architectural language and material expression. And in the foreground, we see, of course, a very wooded kind of shaded area, trees, grass, even plantings in front of the existing building. So a lot of attention to nature, the natural environment. And in the middle, we have this somewhat monolithic concrete intervention. Uh, so we think about that, like I said, somewhat monolithic concrete intervention, and we also think about how can it not be so monolithic? How can we bring some of the richness of texture of the surrounding environment to that intervention and really begin to bring out some of its character in that way? So as we can see here on the right, the set is very much poised for an acceptance and a celebration of the forest, of the wooded area, as I mentioned. So we see a lot of grass, we see a lot of trees, and we see that the buildings just kind of are nestled in between them. There's no really large clearings, or rather artificial large clearings. There's just buildings and situated really nestled again into the site. And of course, the addition does the same. It's very much a connector programmatically between these existing buildings. It's a connector also formalistically and just aesthetically, spatially as well. Um, it's a bridge, not just between buildings, but again between the environment and the architecture. So on the left, we see the expression of that. Concrete has the potential to be a very monolithic material, very stoic, very cold. Again, because of my background, I I always think of the Soviet apartment buildings that I grew up in. These kind of just blocks of concrete, Corbusian-looking things, kind of scary and intimidating looking in that monolithic way. So to avoid that, we uh, just bring in some of the natural environments which already have some of that texture and richness in themselves. We invite them into our process and we let them inform the process and our result. And we gravitated towards board formed concrete, which again, just very, very explicitly, even in this case, takes that natural texture and applies it to our material. So again, this is just exterior shot, and I really think that this underscores the previous statement. Just looking at this facade here on the left and that tree bark right in front of it, we see that that texture is very similar when that light is hitting that concrete. Um, uh, very, very evocative of that tree. And when we kind of step back and look at the building as a whole, we can also recognize that it isn't so monolithic. We see that the different treatments of the individual surfaces really help break it up and bring some interest and dynamicism to that aesthetic. So this is just a couple of shots of the interior here, um, showing how the same treatment was applied all around the building. And what's very interesting about that, of course, is that these are elements done by different trades, right? So the precast soffit that we see here in the middle and the site cast wall are not done by the same people in the field. They are both concrete, but there's a specialist in site cast concrete and there's a specialist in precast concrete, and they're very rarely the same person. So the question is, how do we get a uniform result, interior, exterior, and really all around, with a texture which is so dynamic and so different, has the potential to be so different in every different application? So a traditional process looks something like this for a board formed application. You write your specifications, right? Those are very verbose, very explicit in explaining what you want to do. After you submit your construction documents, you get some shop drawings for review back from your subcontractor. They may be they may be good, they might not, right? You review them. Um, and lastly, you get the site mock-ups, again, for review. Now, the problem with these at every stage is that, like the diagram says, the specifications are not spatial. They are not tied to your design in context. They're not tied to the building process in context. The shop drawings are lacking in texture. They lack some of that tactility, some of that communicative evocative nature of perhaps a mock-up or something like that. And the site mock-ups are out of scale, and really they're just one-off pieces. Just because the mock-up looks very good does not mean that the entire building is going to look good, because again, it's just a piece. How you put that piece together into a cohesive thing is very difficult, right? The piece can be executed perfectly, but the cohesive thing is hard to achieve. So there's really three categories in thinking of something like this for us. It's the aesthetics, of course. It's the constructability and the legibility. How do we want to structure our communication of this intent with respect to these three criteria? And the initial temptation might be to just immediately jump for that script, right? I mean, we love design computation, we love Dynamo, we love Grasshopper. That's why we're here talking about this. But instead, we try to first play with the materials and let that inform our scripting, let that inform our process. So play with the materials, see what the materials want to do, see what we think that they want to do and what we like to see them doing, and then extract some set of rules or some set of assumptions that we can then use as a starting point for our computational investigation. So that's exactly what we did here. We have some prototypes, some mock-ups, some just tests playing around. And we came up with some very initial assumptions of what we like and what we don't like in terms of creating that dynamic and diverse facade aesthetic that's otherwise somewhat hard to communicate, right? How do you communicate randomness? How do you communicate randomness in the field, right? Because it's very easy in a Dynamo or a Grasshopper. You just say, oh, random, shuffle, great. But what does that mean in the field? How much time does that take in the field? It's a pretty big question, right? And so the script, of course, allowed us to also play around with a lot of different configurations and play around with them in context. This is an unwrapped elevation of the building here, and we can begin to see how things appear together, right? Because a mock-up would just show us maybe a portion of this, but this lets us show how they begin to come together and whether the stitching and the relationship between them is something we want or we don't want. Yeah. And again, because it's in that context, we can also directly explore it in the model. And, in tandem with the elevations, basically have a rendering to be evaluating at any given time what we like, what we don't like, how it looks, how does it feel, how does it react to the sun, different parts of the day, any other kind of questions that we might want to interrogate a bit. And so this is really what this looks like. On the left, we have an output of the script, very explicit diagram. In the middle, we have what that translates to in terms of boards in the field. And on the right, we have the finished product, the board formed concrete. That's a resultant of the script and of those boards that were used to make the formwork. So what does that look like in the field? So on the left, we have the quote-unquote shop drawings that were made by the subcontractor. But again, in this case, we proved the value of our script and our process to the contractor in order to make this relationship possible. We showed them what we were thinking about, and they immediately recognized that this has the potential to save time in the field, to save material in the field, and basically translate that to some savings which we can realize somewhere else, right? Because it's one thing to just tell somebody in the field, hey, make some random board-formed elements, and the person then has to figure that out themselves, right? And they don't have a lot of time on site in the field. They need to be moving. So the easier that you can make things for them, and the not just the easier, but the simplest, the lowest common denominator you can find for communicating intent in a way that makes sense is really your best bet. So again, in this case, the contractor realized that this can save time, some material. So they took our diagrams and they didn't recreate them from scratch as you would normally do with shop drawings. They didn't start from ground zero. They took our diagrams just threw them in CAD really quickly, changed the colors up, did some of their own notations, and started running with that. So in the middle, we have the actual form work, and on the right, we have the process. So what's happening is the guy up top is putting on the boards, and the guy on the bottom is just giving him the boards in a very paint by numbers kind of fashion. He's looking at the drawing. He knows what board is up next, and he's just giving it to the installer up top who's laying it down. And it's pretty simple, right? Those guys don't have to ask very many questions. They understand the drawing. It's clear in terms of dimensions. It's clear in terms of color. And that really is the only way that's truly evidenced is in the final product, which I think, as we saw, is quite a refined execution of board formed concrete, which is really much easier said than done. Concrete is a deceptively simple material, especially when you try to apply a very specific treatment to it. So obviously huge credit to the installers, but it was very much the nature of our relationship, our collaborative relationship with the contractor, the subcontractors, which allowed for this to happen. So now we're going to jump into a demonstration of some node-based code. In the advanced portion of our Dynamo user group meetings, we like to typically do this, and this is no exception. So we are going to look at a masonry application of tiling bricks, and we're going to look at what it means to embed some architectural intelligence in the code. So there's a couple of things that I want to talk about in something like this. I want to just talk about some general setup, how we can think about that. I want to talk about what it means to, again, embed that intelligence into a format like coding or visual scripting. Then we're going to check out a cool feature that Dynamo has called Node to Code. And last but not least, we're going to take a look at some peculiarities of DesignScript, which is the Autodesk language for creating geometry and logic and so on and so forth within Dynamo. Okay, so let's start with this here. We can see in the background here, we have a little bit of a preview. The script is definitely past an initial point of development, but it's absolutely not refined at all. A little bit of context for this. So our design computation director, Christopher Connick, actually put together a very quick 15-minute version of this in Grasshopper earlier this week. And then I kind of took some interest in it, in applying it to Dynamo, not just to have it in both versions, but to see how Dynamo can be different than Grasshopper, and how some things might even be different that we didn't expect to be different, like creating geometry or creating logic. So I thought it would be an interesting exploration to do kind of the same thing, but in Dynamo, and see what we can get. So on the left-hand side here, we have our setup, right? So for those of us that are pretty familiar with Dynamo, we know how the nodes work: inputs on the left, outputs on the right, similar to Grasshopper, of course. And we first start with our canvas. So we need to have some kind of general information about the footprint that we want to work with when we're tiling our bricks, right? So I like to start with just a base rectangle, and this is what it looks like. So next we have our inputs, and I like to really just start with the knowns. Just start with everything that I want to use as an input, as basic and as simple as it may look, right? So when it comes to bricks, there's some things that I know, right? I know that I want to be able to specify grout, the grout width. I know that I want to be able to input some kind of patterns for bricks. I know that I want to be able to say, how many bricks do I want of a certain size, and what kind of color do I want? And I also know that I might want the flexibility to change that up and to play around with the rules and to add more or add less, as the case may be. as we're kind of seeing here. So I like to kind of start, of course it is. So I like to start again with the knowns and just kind of putting it all into a kitchen sink, for lack of a better word. I don't know why it doesn't want to cooperate with me right now, specifically on some of these, but okay, sure. But you get the idea. Maybe we don't get the idea. Okay, all right. We'll interrogate that later. Let's see here. Okay, so that works. So funny business. All right. Okay. So we have our kitchen sink of inputs, and this is basically indicative of that. We're just kind of joining everything into one glob of information. We have our canvas, and then we want to start working with that stuff. So the first step is to start splitting up our rules into chunks that Dynamo can work with. And I don't want to spend too much time on this code here. I just want to say that this is where that happens. This is where that parsing happens. So from this kind of kitchen sink of inputs, we do some coding to separate it into information. This is Python specific. You can do this in design script. You can do it in Python or whatever you want. But this isn't really kind of the point of what we're looking at. This is just to say that we split up the rules at a certain point. You can do this with nodes as well. So the next step, once we split up our rules into chunks of information we can work with, aka numbers or words, we then have to start creating some of that logic, right? Some of that architectural intelligence, which is turned into computational intelligence. What does that look like? So this is a Python script. This is the things I'm going to talk about are Python specific for the moment. So when we're in Dynamo, we start with some things that are givens, right? So every time you write Python in Dynamo, you're probably going to need these lines. Import common language runtime, add reference proto-geometry, and we're going to need to import the geometry portion of design script. Next portion, we have our inputs, and this is how we define inputs in Dynamo. Rather than right-clicking here and renaming these guys, we define them in this way. We say that int sub 0 is our rules array, int sub 1 is our horizontal course, int sub 2 is our vertical course. Next, we define some variables. Again, I like to start with the known. So we're working with masonry. What are some things that we know that we're going to need and we know that are going to be important? So the horizontal length of our canvas, so that's what we do. Vertical length of our canvas or wall, whatever. We also need that. And we're going to need a start point. So that's what we do. And this is all this is saying here is in that horizontal line, give me absolutely the first point in that line. Next, what I like to do is set up my counters. So there's some things that we know that we're going to either need to keep tally of, keep track of, or things that we're going to need to cycle through. So I create some counters, typically starting at 0, right? So we're going to want to know how much horizontal distance we traverse with our masonry. Same thing with the vertical distance. We're also going to need to keep track of our masonry rules, right? Because here we want the flexibility to take away rules or to add rules, and so we need to keep track of that. And then last but not least, we want to keep track of our bricks and what we're putting down, just in general, useful practice. Next, we set up our expected containers. So this is another layer which may be a little bit harder if you're just starting out, but sooner or later you kind of start to expect certain types of containers, for lack of a better word. So here in Python, this is how we define an empty list. So we're going to want to keep track of our horizontal modules, vertical modules. We're going to want a list of colors. We're going to want a list of points. We're going to want a list of bricks. And it's a good practice to keep a list, just an empty list called debug, where you can throw some things that you want to interrogate from your script. So the question is, how do I know I'm going to need some of these lists, right? Well, it does come with practice, and it does come a little bit with knowing the way that you work. So for example, myself, when I do this kind of geometry, I know that I like to work with points. So I almost always create an empty point list that I know I'm going to append to. So next, we start breaking things up a little bit more. And I want to highlight that all of this so far is just things that we know, givens. So this long wall of text might look intimidating, but really all of this is stuff that we already know. And the logic is just this short portion right here. It's really not a lot. So let's get into it. We have the spacing. We have a portion here that is called spacing modules. So what does that do? This is how you set up a loop in Python. So you say, for every rule in our array of rules, we want to extract some information. We want to get a horizontal dimension, we want to get a vertical dimension, and we want to get a grout dimension. And the way that we do that is we say, again, for every rule in the array of rules, and then this is how we query individual rules or individual or sub-members of nested lists. This is a syntax which is definitely specific to Python, but is also in design script. And we can see that actually here, we can see what that looks like. So we see here that this output is something like this. We have nested lists, lists, and lists. You see that when I'm clicking here, there's multiple levels that I can drop down on. And this syntax is basically saying, give me the first item of that list. And if I was to then go one step further and do it, the second item of that list, if I was to then say, give me the first item of this new list, and now we see it just gives us that first point, which was at index 0, right? So this is all that that's doing us, and I like to at least explicitly define it in variables so that I know what this is, because right now this could be absolutely anything. I mean, this could be just a list within lists, right? I have no idea what this is, but defining it in this way gives me a clue. Okay, so once we define this for ourselves and we know what our variables are, we add it to our lists. So to the horizontal module lists, we apply the horizontal dimension plus the grout dimension. We say the same thing for the vertical module list. We just do it with the vertical dimension. And again, that's some implicit knowledge that we have for masonry, right? A module, or at least in the way that this script thinks about it, is a brick and a grout, a brick and a grout. So after we have that, we then move on to our actual loop for creating our points or our grid for putting these bricks in place. So let's take a look at that. But first, let's see if I can see these horizontal modules here. 1 second. Okay, so this portion, the horizontal and vertical modules, this is essentially what it looks like. So we have right now 4 unique rules, and let me actually do it for the horizontal. Oops. We have 4 unique rules, and we can see that, right, we have some bricks that are exactly the same size, and then 1 brick which is much larger, and this is essentially what our modules list looks like. It's recognizing that we have 1, 2, 3 bricks the same size, and this guy is a little bit larger. And again, this is a combination of the brick width and one instance of the grout width. So let's talk about our loop here. We set up a loop to iterate through our information and create our grid. So what we say is, while the length that we've traversed vertically is less than the length of our vertical wall, we want to continue running our script, right? And that kind of makes sense because that's how we build a masonry wall. We start at the bottom and we move up. When we reach the top, we stop. So very same way we're going to build our script here. So first, let's work with our spacing rules. We know that we have, right, more than one rule, okay? So we're going to need to extract the relevant information from our module list based on the current rule count. And remember, we set up our current rule count right here. So we start at rule number 0, which is the first rule. So we get a horizontal spacing rule, we get a vertical spacing rule. We do the same thing for the color. We know that in our rules array, there is certain information about the color at a certain point in the lists or the nested lists. So we go ahead and define that, and we append it to our list of colors. And then we move on to create the points for the bricks. So we say that we need a point. We create a point, and a point wants to be created with an X and a Y. So for the X, we use the distance that we've traversed horizontally, and for the Y, we use the distance that we've traversed vertically. This is actually a pretty elegant example. Again, got to give the credit to Christopher Connick here, Design Computation Director. It's a pretty elegant way of thinking of how you can use the lowest common denominator of information to create something else. So it's a point, right? It's a point. It's not a rectangle. It's not a three-dimensional brick. It's a point, and it's created by an X and a Y, which are just integers which we already have because of our loop and because of our understanding of the way masonry works. So you're not taxing your script with a lot of extra computation, a lot of extra processing. You're really making the most out of as least as you can, for lack of a better explanation. And I think that's a very good approach. So when we have that point, we add it to our point list. Now here we go to the next portion, right? Because we still haven't added the part about how we know masonry is built up. So we start with our rules for traversing horizontally and traversing vertically. So we know that our horizontal traverse distance is going to be equal to itself plus the current spacing rule. And in Python, this is just a shorthand syntax for that. This is saying horizontal traversed equals horizontal traversed plus the spacing rule. Next, we, of course, count our bricks. We do the same thing. We say to the current brick count, add one more, because we've just added a brick. Excuse me. Same thing to the spacing rule. We have just cycled through a spacing rule, so we add one more to that count. And next, we jump into some conditionals, which have to do with how we build up that masonry wall. So we know that if we've traversed a certain horizontal distance, if that is greater than the horizontal length of our wall, then we should start our horizontal count from 0, right? Because if we're building a wall in real life and we have a plan to go off of, we have to make a 20-foot wall, right? You lay a course of brick. When you reach the end of that 20 feet, you don't keep going another 20 feet. You start horizontally from the beginning. You just go up, right? So we start the horizontal count from scratch, and we add distance to the vertical traverse distance, and we add that vertical spacing rule to the vertical traverse distance. And to the brick list, we append the count of bricks. Yeah. So last kind of conditional, we say if the current count of the spacing rule is greater than the amount of spacing rules, start the spacing rule count from 0. So this basically all this is doing is ensuring that our rules cycle, that once we reached our last rule, we start from the first rule all over again, and we keep cycling, and we know that it's cycling because when we look at this here, we can see some of this banding, right? That means that it's successfully cycling, because if we were just creating a course of brick and translating it up, this would be entirely vertical and there'd be no banding, right? Because it wouldn't be cycling, it would just be consistently applying that rather than looping. And that's something that Python does for you that Dynamo doesn't necessarily do. Well, it doesn't do natively. You need a Python loop or a design script loop. So last but not least, we define what's coming out. We know that we want some of this stuff to come out so that we can work with it. And in Dynamo, it comes out all together in the out node. And we can, again, use this shorthand syntax to get individual items that we care about. So let's just very quickly play around with some of these rules and just see some outputs of this. Again, very early stage, very quick script. And actually, let me try and do a trick here. Let me try and close this and restart it. Interesting stuff. Right. So again, just playing with this, we can see that it's, of course, definitely not perfect, but it does give us some flexibility to play around and start exploring some of these things. And as we break it, right, as I was kind of breaking it, whoops, oh, gotta break it properly first. As we, of course, now I can't break it, right? Okay, there we go. So as we break it, of course, then it's up to us to go back in the code and interrogate what's going on and which part of our logic is kind of making this happen. And that would happen, of course, at a more later stage, but just for some context here. Okay. So next, the portion that I wanted to talk about is Dynamo's Node to Code feature. So this is exclusive to Dynamo. Grasshopper doesn't have it, and I actually find it to be a very, very useful thing. So we can take at any given time a number of nodes. We can select them. We can right-click Node to Code, and there we go. It just creates some code for us, and that's great. Oops, sorry, didn't mean to freeze that. I need to turn off the preview, and that's great. If you're a beginner, if you're just starting out, this is super helpful. Because you can start to understand what design script is, what it's doing, what it expects, and you can start turning this into your own code. Of course, just keeping in mind that working in code like this is not really a great idea because we have no idea what any of this stuff is, right? We want to write in somewhat logical variables that we can then interrogate and that we can then share, right? Because if a colleague or somebody in another office wants to make some use of this, we want them to be able to contribute in a way that makes sense. And this is not a way that somebody can contribute. This is very much a way that somebody can start jumping in and understanding what you're doing. Some commenting, some logical variables, so on and so forth. But nevertheless, Node to Code features is very useful. So let me show another version of this graph here. This is that same graph, but I've gone ahead and in the middle, excuse me, turned a lot of that jumbo spaghetti, see all that spaghetti, into code, and I've even cleaned up some of the variables. So it's very doable. It doesn't take a lot of time. And the benefit that this gives you is, of course, it cleans up your workspace, right? It gives you some more real estate to work with. We can now see this geometry a little bit better. We know what we're doing. But it also processes faster than native nodes. I'm not sure why that is, but that's the case. And of course, this is just making it a little bit easier if you were to make a custom node, for example. Custom node. Okay, I guess I'm not going to do it right now. But to just copy and paste this code block into the custom node interface, pretty intuitive, pretty easy, and again, processing power boost, and so on and so forth. The other good thing about a code block is that you can interrogate it every step of the way. So you can say, oops, watch. So you can really go line by line and start seeing what's happening line by line. And it's as simple as dragging things to a watch node. So that's really helpful. Again, for a beginner like myself, frankly, it's helpful to interrogate a script every step of the way, especially given that Dynamo's native Python editor is not really all that powerful. You can see here I'm doing a Python script from string, but you can just as easily do something like this. You can do the native Python block, which is it gives you well, it gives you some how you say it? Gives you the coloration that comes with Python syntax, right? It gives you some autocomplete, but the autocomplete is specific. What do I want to do? Rectangle. The autocomplete or the IntelliSense is specific to design script, not the Python, which isn't necessarily helpful all the time. And also, there's no good way to debug this. You can't really go line by line, so that's a little bit challenging. So just something to think about when working with code blocks, that they do offer you that freedom to step through some of your work. Okay, so the next portion that I just wanted to briefly mention is some peculiarities of design script. Because we took a look at a loop in Python, right? We took a look at a while loop. We took a look at a for loop. And here we're actually doing another for loop to create our colors, to apply rather our colors to our geometry. And this is how Python does that loop. For each item in a collection, do something, create a color, blah, 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 add that color to a list, and that's our loop. This is even a simpler loop. This is just how it looks like. For every item, right, in a range between 0 to 5, add that item to the list, and that's a list of items. So how can we do the same thing in design script? I actually didn't really know that there were loops possible in design script, but it turns out that there are. And this is what it looks like. This is that same loop. Again, you define your empty container. You tell design script that you're going to be doing something. The syntax is very much the same for item in a given range. But here it starts to get a little bit interesting because, at least in my investigation, I haven't been able to find that design script has a list. I find that design script has a dictionary. The dictionary is the container, not a list. So when we add things to that container, it's fine if they're all unique. But if we loop over a collection of colors, for example, which is a large collection, but let's see if I can put this. It's a large collection of colors, but we have duplicate colors. When we loop over that collection, this is the same exact thing here. We see that because it's a dictionary, not a list, it's only appending the unique values, which is a little bit interesting. And again, if there is a list in design script that I just don't know about, somebody please let me know, comment or send an email, do something. I'm a total novice when it comes to design script, but just an interesting thing, and it's also further evidenced by the fact that when you add to that empty collection, you're also giving a key value every time. You're not just you're not just you're not just sorry, you're not just adding an empty thing. And so actually, yeah, okay. This is how design script does a similar loop, but a larger range. So we can see how we can make use of some of the native design script functions here. And what's nice about the code block again is that if we do color, it gives us some of that autocomplete. And if we say, okay, by RGB, and we do the parentheses, it'll start giving us some hints as to how it wants that color created. So that's pretty helpful. Ultimately, though, I prefer doing all of that stuff in a Python node. And the way that you do that is first you just have to make sure you're referencing design script. So import common language runtime, reference proto geometry, make sure you're importing design script, and then add this reference as well, DS core nodes, so that you can get some of that functionality like color, which is actually a part of design script core, not design script geometry. Actually, I don't think this does anything. I could be wrong. Am I? Okay, never mind, I'm wrong. Hold on. Okay, so it's a bit of both. Okay. All right, so it is both. So we have to add the reference to the DS core nodes, but then we also have to do this. We have to actually import everything from design script core. Okay. This was actually a point of frustration for me when I was trying to set this up for the demo, because IntelliSense kept suggesting color, but I actually couldn't use it because I didn't have this as part of my import. So just keep that in mind. So that kind of wraps it up for the Node to Code demo. I just want to wrap up very quickly by talking about some resources that are available. Of course, I have to now swap presenter. Just want to talk about some resources which are available to everyone that may be interested in Dynamo. So, of course, Dynamo Primer, Dynamo Dictionary on the Autodesk website, very, very useful. The dictionary lets you get some very specific information about specific nodes, and the primer is kind of a very in-depth introductory guide about working with Dynamo. Introductory videos, again, on the Autodesk website. They have advanced, they have beginner. And for reference, this presentation is going to be hosted on the Philadelphia Dynamo User Group website. These links right now, as I'm hovering over them, you can see that they are live links, so you should be able to make use of that. Click directly. Same with these blogs, they're live links. All of these blogs are very, very good resources, maintained by practitioners, maintained by active Dynamo community members. Of course, shout out to our San Francisco Dynamo user group colleagues. They have a great website as well. Not necessarily a blog, but just a website, kind of like we do, to host their content, their meetings. And of course, Autodesk University, massive, massive resource for everything Dynamo, Revit, and everything else in the Autodesk suite. Revit Beyond BIM. Again, great case studies. Parametric Monkey really stands out, I think, to me in bridging some of the gap between Grasshopper and Dynamo and some of those concepts. It's not really AEC specific. It kind of jumps all over the place, which is nice, and building up some familiarity with that. So I highly recommend checking that out as well. So that is the end of it. And I hope that this was actually recorded successfully this time. So if anybody is interested in following up with any of this work, or just have any questions in general, don't hesitate to contact us through our contact page online. And yeah, we'll do our best to get back to you. Thank you, everybody, for tuning in, and have a good one.